Hello everyone. In this video we're going to be running through a window-to-wall sensitivity analysis using Ladybug and Honeybee. This is the same example that we've been going over in the class, and I hope this video can help as a reference while you investigate your own projects. First things first, we're going to open Rhino and Grasshopper and open up the Honeybee energy model Grasshopper definition I've provided to you. In Rhino, we're going to make sure we're in the right units. We want to be in feet, so we can change that by right-clicking, and from the drop-down menu here, setting it to feet. I'm going to maximize the perspective viewport, and I'm going to build the building by creating two boxes. I will first type in the command line box, set the first point of the footprint at the origin, and set the second corner by typing in 140, 50. And then we're going to set the height to 15 feet. I'm going to change the viewport appearance to ghosted so we can see the surfaces by right-clicking on the name and selecting ghosted. I'm next going to make the second floor of our building by copying this box up. I will type in copy in the command line and simply drag and place another box on top of the first. I'm doing this by snapping to the bottom corner and then to the top corner of the box we created. You'll need to have OSnap on. Be sure to check and toggle this option if you need to. Now that we have these two boxes, which will represent the first and second floor of our building, we need to reference them into Grasshopper. We'll do that by setting them to this brep component. But first, let's review the components here at the top. We've got the Ladybug and Honeybee components that are common to every definition. We next have download EPW, that when this button is pressed will take you to a website where you can search for and discover different weather files across the globe. I'm zooming in to Portland, Oregon. And rather than download, I will copy the URL of the weather file by clicking here, and then going back into Grasshopper, double-clicking into this panel and pasting that link. This link takes me to a zipped file. Because the information in a zipped file is compressed, it will not be able to be read by our definition. So I need to go back, zoom in a little bit more, and pick a slightly different EPW. I am going to copy that URL and paste it into the panel. We can see that this is not a zip file. Next, we will specify an analysis period for our simulation, which right now is set for the whole year. Next, we will set those boxes in Rhino to Grasshopper by right-clicking on the brep component, selecting Set Multiple breps, and selecting those boxes in Rhino. In order for the series of Honeybee components that we have here to run, we need to set this initial toggle to true. This first component will split our boxes into zones according to what can be considered perimeter and core. Following that, Mass2 zones allow us to set the building program, which include occupancy, schedule, equipment loads, and so on. After that, solve adjacencies, which will remove any coplanar surfaces. In an energy model, the envelope is very important to its consideration, and those coplanar elements are often interior and less consequential in energy modeling simulations. After solve adjacencies, the geometry will go into a glazing creator component, and it's here that we are setting our window to wall ratios. Currently, everything is set at 30%, which is the baseline specified by the ASHRAE standard we're using. We can increase and decrease the window to wall ratio by adjusting these sliders. We can break up the overall surface area of the window into smaller openings or into a singular opening by using this toggle and setting it to true or false. After creating the glazing, I suggest we decompose by type to understand that each surface has been appropriately assigned. If we are satisfied with the way things look, we can run a simple energy model by setting this toggle to true. In our case, we've run into an error. We can click the message balloon here to understand what went wrong. In our case, because we changed the units earlier, we need to recompute the canvas. And we can do that by right-clicking the canvas and selecting Recompute. If we've done everything correctly, our simulation should begin to run, and we should see this window pop up. After this simulation is complete, some values will be returned into Grasshopper. Down below, this is a honeybee component that will color the zones in our model according to their values. We have it connected to total thermal load, so when we set this toggle to true, those in blue are incurring less of a thermal load than those that are red. In this simulation, the second floor west zone is incurring the most thermal load. Up at the top, we're doing a little bit of math to report the total square footage of our building and the total energy use, and we're dividing one by the other in order to return our predicted energy use intensity. Here we have some graphs of the cooling and heating values from the output of our simulation. Over the x-axis of the graph are the months of the year. The top graph can help us understand the cooling load throughout the year, and the bottom graph can help us understand the heating load throughout the year. We should record these values before making changes to the input of the energy simulation. Before making changes, I should set this toggle to false, or I can right-click on the canvas and simply lock the solver in Grasshopper. I'm going to slide over to the glazing creator and make some adjustments to the west elevation window-to-wall ratio. I'll double-click the slider and type in 0.2. Again, record the values before initiating another simulation. I'm going to right-click the canvas and toggle on the Grasshopper solver, which should run another simulation. Once that simulation is completed, we'll go ahead and take a look at those values and record those results, including overall energy use intensity and those loads that are specific to cooling and heating. Next, I'm going to change the window-to-wall ratio on the west elevation, this time to 40%. The simulation will run again, and we will again take a look at the results and record them. In this video, we've run simulations with the window-to-wall ratio on the west elevation at 20%, 30%, and 40%, and I have recorded those predicted EUI values. I have gone on to adjust the window-to-wall ratios from 20% to 80% on all of the elevations and graph them here. We can see from this graph that adjustments to the window-to-wall ratio on the south lead to larger increases in the thermal load, while adjustments on the east have less effect on the overall thermal load. I hope this video will be helpful as you run through a similar process interrogating your building and climate. If you have any trouble, please feel free to email me.